this lecture to go a little bit deeper on what is actually a Markov equivalence class. So this MEC is just a acronym for Markov equivalence class. And then we will need to learn something that we call ancestral graph. So this is a necessary concept to define Markov equivalence classes for the case of we have unmeasured confounders. We call it semi-Markov models. So before starting, I also want to clarify what's the importance of the unmeasured confounders. So when you have all the variables, so we have the u's and the v's, they are all observed. Suppose you have all the variables. Then the causal diagram that we defined is basically the projection when you remove the u's, right? So the causal diagram, as I defined, is already a projection of the supermodel where you have all the variables observed. So if you draw the diagram, I think in the exercise sheet you did this. If you draw the diagram over the v's and the u's, then this graph can be converted to the unmeasured confounding case or the semi-Markovian case by considering bidirected edges representing the variables u's, because the u's are not observed anymore. However, you can do the same procedure for any variable. You can convert any variable to an unobserved one, so you just move it to the set U, and then that is something that we call projection. So once you have the graph over a set V, you can create a projection of this graph over V now over a subset of V, for example V prime, and this graph is valid to the in the sense of representing the probability PV prime, the probability of the subset of the variables that we're talking about. And not only the projection works for probabilistic reasoning, but also for causal reasonings. So that's why unmeasured confoundings are not anymore an issue when you work with semi-Markovian models. You can consider any subset of variables that you either have available or you want to have available. So it doesn't matter the subset that you are choosing to work on. The graph over it's still a valid one. And this is actually formalized in something that we call latent projection. So the definition of latent projection is just, so you get a graph. I'm calling here DAG and ADMG, but remember, actually this is already a graph that satisfies the Markov condition, so that's a probabilistic model. It's not just a graph. It's just, now I'm using as a synonym. So if I have a DAG or a ADMG that's over a set of variables V, for any subset V prime of V, we have this projection, and this projection is going to be denoted by this bracket here, and it's going to be defined as the following. First, I don't know why the graph is not appearing. Let's show the graph here. So first, for every edge Vi to Vj, if this edge was in G here, right? But no other variable on this path. So that is a path. So this is not actually an edge. So this is a path. So suppose that is a path from Vi to Vj. And this is in the original graph G. And if there is no other variable in this path that's in V prime, then we will have to add the edge Vi Vj to the subgraph over V prime. Let me just show here the example. So we have A, W, X, Y, and Z as the original set of variables. And this is the graph. Suppose that now I want to write the projection of this graph just over Z, X, and Y. Okay, so for some reason I don't want to use A and W anymore. So what is the graph that represents the original model? So it is still representing the original model, and more importantly, is representing the original probability of X, Z, and Y, the marginal distribution, But what's the graph? How can I form this graph? So from x to z, I'm going to add an edge from x to z if that exists a path from x to z, and that is, right? So it's from here to here, there's this directed path, and all the variables in this path are not part of my v prime, so I'm removing it. So the idea is to preserve connections. So I have to preserve this directed path. So I'm going to add this edge from x to z. And this is important for you to know, because every time that we have an edge in a causal diagram, this doesn't mean a direct function relationship, or it is after you substitute all the variables that are part of all intermediate variables that are here. So in the exercise sheet, you also did something like this. I asked you, let's remove the z. And what's the probability between x, y, and only the u's? When you do this, basically you are replacing the z's with the u's variables, and then you kind of create a new function for example, in this case, z is a function of a. But once you remove the a, now z is going to be a function of x by just substituting a as a function of x, right? So you just create a new function for z that's now with the argument being x. So this is directly, you can convert this directly in this projection by just following directed paths. If it's a directed path here, you can add an edge here. What about between z and y? What do you think is going to happen here?
You have a path y, a, z, and a is not in v prime, therefore you have a graph going from y to z.
Exactly. That's it. There is now the second part. Okay, so between x and y, we don't have any path, directed path, so we keep it like this. So we go to the second part, which is about the bidirected edges. We are going to add a bidirected edge between vi and vj if then in the original graph there is an open path that's into vi and into vj. We call it as a confounding path. So for example, between x, w, so the path x, w, and z, it's forming or divergent path. So it's both into x, so there is an arrowhead in x, and it's also an arrowhead in z. And it's open because it's a non collider there. So it's a path that's creating a confounding between x and z. And this path, once you remove the w, so as long as there's no other variable in the graph that's in this path, this has to be converted as a bidirected edge. So between x and z, now we are going to have a bidirected edge. I think that's hopefully x and z. Okay, I put the x and z first. X and z, that's what I talked about. So x and z exactly is what I was talking about. So we have now a bidirected edge between x and z. What about z, x and y? Let's see x and y.
There's no edge going into y, so we know that it can't be.
Exactly. So there's nothing between x and y. What about y and z?
Same reason.
Y and z. So yes, so there's no into y, so there's nothing. So this is done. Oops. I don't remember what I did here. So that's the result. The result is that anything that you derive from the projection is valid on G. So it's because it's weaker, right? So if you can get any result from G over V prime, this result is going to be true even if you don't have the G, it's going to be true on G, and it's going to be true on the true model as well. But of course, not everything that you could get from G, you will be able to get from G over V prime. It's just weaker, right? You are working on a subset of variables, so you have more confounding, you don't have ways to condition on different variables. So of course you have less information, but if you have anything derived from this projection, you can be sure that's going to be working on the original graph.
I have actually two questions. First, between y and z, directional to Z.
Y, Z,
Y A, Y directional to Z.
right.
And then Y with.
So it's no longer necessary because, so if you follow these two steps, it's not going to create any path here. Oops. Because if you see the meaning, this path here, the confounding between A and Z is not creating confounding between Z and X because this path is blocked. Also, this path here is not creating confounding between Y and Z because it's blocked. So it's irrelevant.
Why is blocked?
There's no arrow.
There
in
is
Y.
this collider on A, so the information from Y is not arriving on Z.
But if you move A, it's not no longer in B prime, right?
Yeah,
Like gone.
you're not conditioning on A. Actually, it's gone.
Oh.
So you're not touching on A. So A is never part of any conditioning set. So by removing A, this path here was irrelevant before. So it's not creating any association with other variables, right?
What do you mean by open path?
Open in the sense of the separation. So by being not blocked, right? Or
What
they're
you
not.
have already explained. Okay, thank you.
All right, and this is kind of the same. So if the probability that, so if the graph was satisfying the Markov condition for some probability distribution PV, the projection is also going to satisfy the Markov condition to PV prime, right? So is what I said about being probabilistic, faithful to the original model. When we write the factorization, so this is just an example of how can we actually see this consistency, or this how we are preserving the representation of the joint probability. So here we know that we can factorize the probability PV, or where P is the whole set, as the product of the variables given the extended parents, right? Just remember, so I'm going a bit fast here, you know already what is this, but this would be the extended, the factorization using the chain rule. And once I think it's already simplified. So it's already simplified. So once you have the extended parents, you are going to have these variables here. So just an example, for Z, the extended parents are the parents of all variables that are part of the confounding the confounding component. So Z, the confounding components, Z and A. So the parents of A is X and Y. So that's why we have X and Y. And also Z is a parent, so we add here A, Z, A, X and Y is just the part of the A that's part of the C component, and then the W is just another parent. So this is just already the factorization of PV, where V is A, W, X, Y, and Z, given according to the extended parents. Now, if we consider, this is just a copy, so you can have a reference. So if we consider a subset V prime, what will happen is that we take here the same factorization now according to the extended parents of this graph, and then we're going to see another one. And I'm showing now how can you compare, saying that both are exactly the same. So from this left side, we know that this is the PV, and the probability of PV prime is just summing over the variables that we are removing, right? Then we can do this with it's missing one term here. Oh, sorry. ZA. Oh, no, sorry, I'm just combining both. I think it's me. Yes, exactly. So what I did here is just I put together this. So if you put together again using the conditional dependencies, and then you just put and use the Bayes theorem to simplify this as a joint of Z, A, and W, you see that this is equivalent, and then this is just a copy. And since we are summing over the A and W, these two variables are going to be out, and this is going to be exactly the same as this, right? So this is exactly as the same. So I'm just showing that the factorization over the extended parents in the projection represents exactly the probability of V prime, and this is the same distribution that I was talking about before, right? This is exactly this, the sum over A and W of PV. So we are not losing information by considering this projection if you consider this procedure. All right. Now I want to move to the next topic. Yeah, this is I just explained, saying that the independencies that all independence relations that are implied by the projection are also implied by the original graph. Of course, that not all implied from here, from G, is going to be in G V prime, but everything that you can extract from G V prime is going to be from valid on G. And now, given this, I think we can move a bit more deep on what is a Markov equivalence class. So you understand why why causal inference is challenging, right? So the idea is not trying to recover the functional model, the structure causal model, but we can work on the level of the structure of the model. However, by considering the structure, we also are considering many equivalent models. This is something that I showed you in the previous lecture. Basically, like the same probability distribution. If you are under the scenario that the only information that you have available is the probability distribution, the observational distribution, there are many models that actually are representing the same set of conditional independencies, which is what you can actually extract from the observational distribution. So remember that we considered several factorizations of the joint distribution, and this could lead to different models. Like these three graphs, they are derived from different factorizations of the same joint distribution, and applying only the independence of x and y given z. So you could create three different models that represents only the independence of x and y given z. So they are all implying the same set of condition dependence. In this case, it's just one. This is the other graph that we saw in the previous lecture. And this is kind of a very hard way of actually detecting what are the models that are compatible with some distribution. So if I ask you, please list all the graphs that could represent a set of condition dependence, for example, x dependent of y given z, just one element, it take a long time for you to actually list or factorize all possibilities, see if you can actually apply the independence and simplify it, and see what are the resulting graphs. And this is actually, we can count how many possibilities you can factorize and check how many of these diagrams you can compute. So the number of diagrams that exist over any variables is given by this formula, and it's super exponential to the number of vertices. And this is just a table for you to have a notion. So imagine, like, if I ask you for write all the possible factorizations or DAGs over two variables, is 3, right? So the empty, then one in one side, and the other pointing to the other direction. Because here there's no unmeasured confounding, right? So we are in the situation of DAGs. If now I ask you to draw all possibilities among 3 variables, it's already 27. With 4, 729. With 5, it's almost 60,000. And 6 is already to the 10 of to the power of 7, and then this is super exponential. So it's impossible. So that's the idea. We cannot ask you to list all the possible diagrams and see what are those that are matching to the condition dependencies that I'm talking about, and see what are those that are part of one equivalence class. So that's not the way that you should go. Sorry.
For n equal to 2, there are 3 different DAGs.
For 3.
It was
For 2. Oh, 2, 3, yes.
And this is one, for example, A to B, B to A, and that's the 2.
And the empty one. Yeah, A and B is completely connected. And then you would check if ever all these 3 are part of the same equivalence class. This would be impossible to do. That is even this recurrency relation that was written by Robson. So it explodes really fast. So the way to check, so people started creating some graphical criteria. So of course, this is not the way to list everything, but it's a good condition to check if 2 modules automatically are part of the same equivalence class. So again, this is in the Markovian case, or no unmeasured confounding. So that is this result by Verma and Pro. It's a very important result that says the following. So 2 different diagrams, DAGs, right, no unmeasured confounder, they are part of the same equivalence class if and only if they have the same skeleton, where skeleton is just the undirected version of the graph. So it's just the same having or not having the edge, and the same V structures. V structures are called also unshielded colliders. So those are variables that are forming a collider, but they are not connected to each other. I can show you an example. So these 3, I'm telling you, that are part of the same class. And it's really easy to see why, because all the 3 have the same skeleton. They all are with X and Z with an edge, Z and Y with an edge, and no edge between X and Y. So they have the same skeleton and no V structure. So a V structure would be 2 variables that are disconnected like this, but the variable in the middle is a collider. So none of these have a collider in the middle. So none of them have a V structure. So they all have the same set of V structures which is the empty set. So this is so same skeleton, no unshielded collider. So they are all part of the equivalence class. Now let's ask about this first 2 here. I ask you, so the only difference is the one in red there. So instead of having A pointing to X, I have X pointing to A, right? And I ask you, are these 2 part of the same equivalence class or not? First question, what about the skeleton? Are they the same? Yes. What about the unshielded colliders? This is not an unshielded collider. This is not an unshielded collider. This is an unshielded collider. So it's a triplet where X and Y are disconnected. So there is no edge between them. So it's a triplet. And the variable in the middle is a collider. So there is one unshielded collider here. This is not an unshielded collider. This is not an unshielded collider. This is not an unshielded collider. So there's only one. What about the other? Exactly the same, because when I changed this direction here, I'm not creating any collider. So this makes this, I don't need to go to write all the factorizations and check what are the independencies, or even apply the separation and see what are the implied condition dependencies through this separation and check if this is the same as this one. You can do it. You can see by this separation, for example, that X and Y are independent given A. Here is the same. X and Y is independent given A. But you don't need this. By using the criterion, you can just say they are implying the same condition independency, so they are equivalent. What about the third one? Is this the same as the, is this the in the same class as the both the first two?
No, they have different mean structures.
Before we had like Z was an unprotected, unshielded collider.
Exactly.
And now Z is not anymore, but now Y is.
Exactly. So Y is an unshielded collider. Z is no longer. It is completely different equivalence class. What about this? Is in a completely different class, is in the same as G3, is in the same as G1 and G2.
3 and 4 are equivalent? Because Y is the unshielded collider?
Yes. So you have one unshielded collider, everything else is no unshielded collider. So if you would consider these two are in the same class but not in the same as the other two. Okay? Then you can kind of define something that we call CPDEG, or completed partially directed and acyclic graph. No one tells this name like this. Everyone says just CPDEG. But it's a representation of all the invariances that you saw before. So, for example, let me go here with an example. So if I have an edge between Vi and Vj saying that Vi points to Vj, this indicates that every DEG in the Markov equivalence class has this edge. It's an invariance. So before, let me just go back here. So before, for sure, I know that this is under no measured confounder, right? So for sure, I know that these two variables are in the same equivalence class because of this criterion. But I know also, and you understand why, that every member of the class of these two, you have Z with Y and X pointing to it, because it's the only way to create collider in this case where there's no unmeasured confounding. So these two edges are going to appear in all members of the class, of this class. However, this edge, X and A, can flip without changing the class. So this is not going to be an invariance in the class, and this is going to be invariance in the class. And that's what the object later is going to capture. So the definition of this class kind of shows only the invariances. So if I have an edge from Vi to Vj, then I have the edge in every member of the class. If I have now an undirected edge between Vi and Vj, then this means that the edge can change. I don't know what is the direction of it. It just could be anyone, and this won't change the class. Okay? So this is an example of a CPDEG. Then I can start listing all the members of the class by looking at this object and just flipping without creating unmeasured, without creating unshielded colliders. So, for example, here I have W pointing to Z. So this for sure, it's here. W pointing to Z, okay? But about the others, in this case, I have all edges connected without creating unshielded triplets. So unshielded triplets is the one where the first and the third are not connected. And here I have, actually I have this. This is unshielded. So X, W, and Y is a triplet that's unshielded. So I can flip the edge between W and X and Y and W as long as I'm not creating an unshielded collider. So I can flip like creating like a fork like this. I could create a chain or change to this other side. As long as I'm not creating a collider and forming an unshielded collider, I'm fine. The same as X, Z, and Y. This is another unshielded triplet, so it cannot be an unshielded collider. So I can flip as long as I'm not creating collider. Here is a collider, but it's not unshielded, so I'm fine with this. So this is part of the class. This is again part of the class, because now the difference here is this edge between Y and Z. Here is Y to Z and Z to Y. I'm not creating collider, unshielded collider.
What's the difference between an unshielded and a shielded collider?
So shielded is because it's a triangle. So triplets is because there are 3 variables, right?
Yeah.
This is unshielded because this edge doesn't exist. So you're not shielding A and C. So if the first and the third variable of the triplet are not adjacent, then it's unshielded triplet.
So this is unshielded.
This is unshielded triplet.
Okay.
So I have unshielded collider, and then I have unshielded, and I can form non-collider. Can flip as long as it's not forming a collider. But it's unshielded because A and C are not connected, directly connected.
If A and C were bidirectionally connected, then it would be shielded.
Yes,
Okay, understand.
not necessarily bidirected. If you have this,
Oh, okay.
it's shielded.
Okay.
It's not forming cycle, right? So this is
Yeah.
something
I
that's,
mean, right now, we're even in the case where we don't have bidirectional, right?
Yes.
Because we're in DAX.
Okay.
yes.
Oh, yeah, yeah, true.
Right. So I can list, so all the graphs, they are all here. I can list all the graphs that are not forming an unshielded triplet, unshielded collider triplet, but I'm keeping the arrowhead into Z here, right? So all they have W pointing to Z, so this is that invariance that appears there. But everything else is flipping as long as it's not violating that condition that I just said. Got it?
But this condition is not written in the definition.
Now that's the definition of what is this object,
Oh,
not on how to list the members of the class. So from this object, I know that what's written is just invariances. So the edge W and Z is going to appear in all the members, while the other, so as I know that there is at least one DAG where the edge in one direction and at least another edge with the other direction. It's just a no invariance, but doesn't explain how to create all the elements of the class. And to create the elements, you need to follow that condition. Okay. Okay, so you can check as well that all, so we represent this, for example, it's just a notation. Maybe if you're going to read a paper, this is a way that we describe that the CP-DAG C is the equivalence class of G1. It's also the equivalence class of G2 and so on. It's just a notation. They are all in the same equivalence class. So we also discussed that the issue of equivalence is much worse when we have a measured confounder. So the class is much bigger, right? Because we now have the possibility of adding these bidirected edges. This is another example where I showed last time that sometimes we have a class where we can see some invariances. So this is an example where Z is still a collider, although I don't know if it actually is Y pointing to Z and X pointing to Z, as the case as we just saw with the Markovian case. So in the semi-Markovian case, it's much more complicated to derive what are the diagrams that are compatible or representing the distribution that we have in hand. And that people already did this, created this formula. So basically the space of this object. So this object is, remember, is called ADMG. So it's a acyclic directed mixed graph. It's just another name. Instead of DAGs, we are calling ADMGs. So the space of all the graphs with bidirected edges is much bigger than the space of DAGs, of course. It's also super exponential, but the formula is this one. So you can see here that's the space of DAGs multiplied by some number here, that's to the power of n. And if we see the numbers, it's like I'm comparing. Here are the DAGs and here are the DMGs. You can see how bigger in comparison to the DAGs the space is. So for example, with 2 variables, instead of 3 DAGs, now we can create 6. With 3 variables instead of 27, now we can have 216. So 3 variables is already a lot to do by hand, right? 4, it's kind of crazy. So with 8 variables is now impossible to do with a computer. So it's again not the way to actually do inferences by listing all of them. To actually make the reasoning with unmeasured confounding possible, they created this object that's called ancestral graph. So an ancestral graph, it's going to be like a representation of many ADMGs. So it's just a simpler representation. So everything that we can represent with an ADMG is going to be in sense of probability distribution. So all the conditional independencies that are implied by ADMD is going to be now represented by this object that's called ancestral graph. So, but that is this collapsing. Many ADMGs are going to be represented by just one ancestral graph M, right? So M. So this is going to be true. So for any ADMG that's part of this box here, we will have that X, for example, this is just an example. If there is an independence between 2 different sets, X and Y given Z, this is going to be present in the representation that we are going to define. It's going to be also present there. So we are going to see how this is going to be preserved. But the important part here is that we are collapsing a few objects in just one, and then the space is going to be reduced because of this, and this is going to help the inferences.
Quick question: all the ADMGs, they're all equivalent with each other, also?
So we are going to have like one object that represents many ADMGs together. So they are going to be all equivalent. So that is this class, this equivalence class. We're going to see this in more details. But all these graphs here, they are already equivalent. Okay. But they are not going to be represented just with one ancestral graph. But a few of them are going to be reduced to one ancestral graph. So we are going to simplify the list. We are going to reduce the number of elements by using this object. Yes. So so that's the idea. So how can we do this in practice, or even like how the theory could be extended to the case of unmeasured confounders was by having this new object that we're going to define that's called ancestral graphs. So to define ancestral graphs, I need, just to clarify here, I need something that's called mixed graph. So nothing crazy, it's just mixed because I have 3 types of edges. Directed, bidirected, and undirected, okay? So we are going to have like a graph that has 3 types of edges.
So is undirected not the same as bidirected?
So we are going now to see a different type of graph that's not ADMG, but because ADMG, so we are talking about just graphs, no probabilistic models. So that is DAG. That is just one type of edge, directed edge. There is also ADMG, a cyclic directed mixed graph, where I have directed edges plus bidirected edges. when I convert this as a probabilistic model, the bidirected edge has the meaning of representing unmeasured confounders. Here we are going to see a different object as an ADMG, but so I'm just talking about what is a graph. I'm not connecting as a probabilistic model yet, but I'm going to connect. And the directed edge, bidirected edge, and the undirected edge can be present. It's just what I'm talking about. There's nothing more than this. So, but I will define how they are now tied with the probability distribution. So, first of all, it's a different graph because we allow undirected edges. Okay?
And also the at most one edge between any two vertices.
Exactly,
Previously
exactly.
we allowed
Exactly. That's perfect. Yes, and there is also this another condition that we can only have one edge between two variables or two nodes here. We're even talking about variables yet. The notion of collider and non-collider are going to be the same, but the undirected edge is going to be two tails, right? So it's just an easy case where, for example, and if I have here examples, yes, I have here examples. So this is a non-collider. Although this is an undirected, doesn't matter. The only thing that matters are the edge marks. As long as the edge marks are not two arrowheads, this is a non-collider. And if it's two arrowheads like this, this is a collider. Okay, so but the definition is the same. So this is a mixed graph. This is, what do you think? It's a mixed graph. This is again mixed graph. What about this? That's the case. So the only thing that I have to care about here is the existence of three different edges, and there's only one type of edge between them.
So if you have a line between X and W instead, that would still be fine?
It's still fine.
Okay.
Yes. Okay. That's not a mixed graph. Triplets, same thing as before. So the active triplets, to extend the concept here of this separation, triplets that are active are those that are either with a non-collider and the non-collider is not part of the set, or is a collider and the collider or the descendant of the collider is part of the set. So the active triplets are before. Just remember that can have undirected edges like this. It's pretty the same, nothing different. The inactive triplets, again, either with the collider or the descendant, and all the colliders and descendants of this collider cannot be part of the set. So the triplet is inactive, or if it's a non-collider, the collider is part of the set to be inactive. So the only difference is the different type of edge here. Okay. So with this, we define something that's called M separation. So M, because it's for mixed graph separation, is the same thing. Just a new name. So that's why I'm going pretty fast here. So this is exactly the same example as before. So if we condition on the empty set, this path is unblocked, right? So there are two triplets. These two triplets are open or active given the empty set. So this whole thing is not disseparated, right? The two verbs. With B, it works. With W, works. If both, works even more. Now, if I have a collider case like this, it's the same. So if we don't condition on the colliders, and then the path is blocked, so X and Y are M separated. With B, I can open one of the triplets while the other is still inactive. So either B or W works, but they both cannot. Okay, so now we define what's an ancestor graph. So an ancestor graph is a mixed graph, but it has to satisfy three additional conditions. First, cannot have cycles as before, directed cycles, but also cannot have an almost directed cycle. An almost directed cycle is a case where I'm going a bit ahead of here with this definition, but it's a case where I have a cycle, but I almost created it. So for example, I have like A pointing to B and pointing to C. A cycle would be C pointing to A. But instead of closing the cycle, I can close it with a bidirected edge. This is an almost cycle, like the last edge would create the cycle if it was in the same direction, but I created a bidirected edge, right? So like this would be also an almost cycle, right? So this is not allowed. You're going to see why later. That's what's written there. But let me continue first. Another thing that's not allowed is that a parent or a spouse so if you have an undirected edge, like V1 and V2 are connected by an undirected edge, you cannot have an arrowhead pointing into V1 or into V2. So this means that if V1 and V2 are connected by an undirected edge, they cannot have parents. So parents would be this case, V1 and V2. V3 is a parent of a variable that's connected by an undirected edge to another one. Or a spouse. This is a spouse. So a variable, so V3 is the spouse of V2 in this first triplet. And this is not allowed because V2 is also connected by an undirected edge with V1. So following these three conditions, what do you think about the first example there?
As a cycle.
Cycle. So not allowed. What about this?
The second one is
Yes.
Almost.
What about this?
the third one.
The third condition. So, and this?
It's again the third.
The second and the third.
Yes.
So there is no cycle. So the cycle would be created. So there's no way to create the cycle. So it would have actually all the path is directed except the last one. So this is not an almost cycle. The undirected edge, there is no arrowhead pointing into the variables with the undirected edge. So this is not violating the third condition as well. So only violates if there is an undirected edge and one of the variables has an arrowhead into this variable. But that is no violation. So that's actually an ancestral graph. And before going to the next, I want to show you why those conditions exist. So the ancestral graph, by the name you can guess, it's representing ancestral relationships. So the edges no longer are only direct in the sense of immediate causes. So as long as a variable has a directed path to the other, it has to be directed this path, but one variable is ancestor of the other, then it's going to be represented in this graph by a directed edge. You understand? So this means Z and X means that Z is an ancestor of X. In the ADMG, here is just collapsing these modules, right? So Z is an ancestor of X, not necessarily through a directed edge, through like one edge only, could be a directed path. Arrowheads mean no ancestrality. So when I say X has an arrowhead here in an edge between Z and X, this says two things. The tail says that the Z is ancestor of X, but the arrowhead says that the X is a non-ancestor of Z. That's the meaning of the arrowhead. So when I say this says that X is no ancestor of Y, and Y is no ancestor of X. So why this is a problem? Because it's saying that X is ancestor of Z, then of W then of Y. So X is ancestor of Y, but this is saying that X, this arrowhead is saying it's not ancestor of Y. So it's a contradiction. So almost cycles are a problem because of this interpretation of the model. Cycles is just because, as before, we were not allowing cycles. And the undirected edges, they are going to represent bias through selection bias. And I'm going to explain later why this can be a problem. I'm late, as before. So I'm going to finish the definition of maximum. I'm going to finish earlier, as I promised you. I'm going to improve. So a maximal ancestor graph is what I need in the end. So that's the last definition about ancestor graph. So ancestor graphs are representing conditional independencies, as I said before, but it's not maximal. So let's read the definition. A maximal ancestor graph is an ancestor graph such that for any two non-adjacent vertices, there is a set of vertices that M separates them. Because I need that the non-adjacency in the graph represents M separation, so they cannot be connected. So in this case here, what do you think that is this like? So first of all, it is an ancestor graph, right? Because there is no almost cycle, no cycle, there's no undirected edge, so there's no violation for the condition 3. But let's try to apply M separation there. And so X and Y, there is no edge between them. Is there like a set that M separates X and Y in this graph? I'm asking you, just use the D separation as you learned before. So X and Y are connected by this triplet with a non-collider 1. So I need to condition on W, right? All right, so what about this other triplet here? Is another triplet with a non-collider. I also need to condition on Z. So with that set Z and W, what happens with all the paths? Then this third path here, there are two colliders. They are going to be open. So there is no way to separate X and Y using M separation, but there is a missing edge. So although it is an ancestor graph, it's not maximal. So that's all the implied. There's no implied independence there. So everything is actually dependent. So to fix it, you would have to add this bidirected edge here because X is not ancestor of Y and Y is not ancestor of X. So this is representing all the ancestralities as before, but it's also maximal in the sense that all the missing edges actually represent a M separation. So in this case, there's no M separation, but it's valid. So there's no missing edge, no way to violate it. So in MAGs, we need that the pairwise Markov property. So that's exactly what the pairwise Markov property says, that for every missing edge, there is a set that M separates them. That's just a name for it. This property is satisfied, right? So the pairwise Markov property that says that every missing edge corresponds to a condition dependence relation is satisfied in a Markov in a maximal ancestor graph. So how can we create then the maximal ancestor graph? So I need to explain. So because of this idea of this, the missing edges have to correspond to a M separation. When I look at the ADMG, at the causal diagram, the original causal diagram, I need to see if the variables could be separated or not. So because this condition doesn't exist in the causal diagram. Remember that we saw some examples where there's no way to separate two variables and the graph was still valid. So there are cases where the two variables are not possible to be separated, but the graph is still valid. But when we move to the maximal ancestor graphs, this cannot happen anymore. So we need to learn what is this inducing paths. So those are paths that are going to represent this type of non-separability between two variables. So in an ADMG, so we have the set of variables V, U. Now we have the set S that I talked about. So these are variables that we call it selection nodes. So suppose that you collected some data, and this data was under some selection bias. So I only collected data on children. So there is a selection bias because there exists this variable that's the age of the person, but the age range, right? Age range, but the age range is only fixed in one particular value, which is children, like from babies to 12 years old, something like this. So I don't have data for all levels of the variable. I just have data for one particular level of the variable. Or for example, I just collected data of human. So I don't have data of man. So the variable gender or sex is actually only fixed on one particular level, that's woman. So the variables, the selection nodes, they are variables that are unobserved, because I don't know what happened when you collect the data, but maybe you guessed because of the collection procedure, but those are variables that you cannot touch it. So it's always conditioned on. So it's always part of the conditioning set. It's kind of you always condition on the fact that the age range is children, something like this. So we have three sets of variables: the V observed, U unobserved, and S is selection variables. And there is this inducing path. This inducing path is a path that I don't like this definition, but you can use it. The easier definition is just that it's a path that has only colliders in the middle. So it's like this. That's the real definition. But you can derive the same thing like this. So I have like A, B, C, and D. Let's put the D here. So it's a path where all variables in the middle of the path are colliders. So could be, so in the case here has to be bidirected, but here could be anything. And all the variables that are except the and every collider on P is an ancestor of X or Y. So this could be an ancestor of this. This could be an ancestor of this. This is creating an almost cycle. Let's put this. This is creating an almost cycle. Let's put this. But anyways, you have like a path, and that's this path here, A, B, C, and D. All variables are colliders, and all the colliders are either ancestor of the first variable or of the last variable. It's like this. If you try to find a separator of A and D, you're never going to find it, because since they are always ancestor, there is always an open path through the ancestrality here, and you have to condition on them. And then once you condition on the variable, you open the collider. And then when you go to the next, you know that's also an ancestor, so there is a directed path, so you have to condition again. And when you condition again, you condition on the next collider, and then you always open the collider path. So that's kind of the way. How you read this? So this is saying that every non-endpoint vertex is on P is either in U. So being in U means that I was defining inducing path in a mag, which exists as well. But we were talking about ADMGs, so this is actually like this. And now that's what I stopped. You could have this as well. So you could have something like this, just to make it clear that this is a ADMG. Okay. Inducing path is also defined in mags, but we were talking about ADMGs. So the idea is that it's a collider path, so that is this path through bidirected path edge. Doesn't matter here that's a bidirected edge or not, but as long as the variables in the middle, they are colliders, and also the colliders are ancestors of the first or the last, then you are creating this inducing path. And the definition is kind of like this, like the variables that are not the first or the end, which are the known endpoint vertices. They are either part of the U, right, like this, or they are colliders. That's what's written there. So you're reading the variables, including the U's in the bidirected edge. But you don't need to think like this, right? You can just think that it's a path, it's a collider path, and the variables that are colliders are either ancestor of the first or the last.
Here in the definition, if every non-endpoint vertex on P is either in U, but U define just edges, not vertex. I think it should be,
It's
to be in U, it should be edge.
H?
Yes, because
No, maybe you can complain about a vertex being a variable, not a vertex, but it's always a vertex as well in the graph. So the U's are all the variables that are not observed. So in the SCM, you have all these variables.
so that means they somehow create an edge between a bidirectional edge between.
Edge, yes. So yes, exactly. So this. So this definition is kind of reading the graph like this.
Maybe
They are equivalent.
Yeah.
So in this case, it's just an ADMG over VU. So yes, maybe you can read
You
like
can
as a
just-
DAG over VU and S.
Yeah, maybe just replacing vertex with edge can be
But an edge can't be a collider, that doesn't make sense.
non-endpoint edge. Yeah.
So the
Then
point is the following, or we read this as a DAG instead of an ADMG,
Mhm.
and then we include the U's as vertices, or you read as an ADMG where we simplify the U's as bidirected edges, and we just need to look at the collider cases. That could be something like this as well, right? Something like this. You don't need like being bidirected, but the variable in the middle is a collider and also is ancestor of one of the variables. So this is another inducing path. So you just need to see that there is a collider path and the variables, all the colliders are ancestors of either the first or the last. So those are examples of inducing paths. So just a bidirected edge is a inducing path. It's the easiest case. That's the selection node. So the selection node is unobserved, so I'm representing here in gray, and is conditioned on. So that's why it's creating association between X and Y, and it's because of this that's the edge between X and Y is undirected. It's kind of you're hitting this, and then it's, in the end there's just tails on this. So it represents the fact that X and Y is associated, and X is ancestor of a selection node or Y, and Y is an ancestor of a selection node or X. Since they are kind of cannot have a cycle, then the only case is that they are associated by a selection node. So that's a representation of an undirected edge in the mag. So that's the case that I just wrote there. So you have all, so the path in green is a collider path, and the variables are all ancestors of either one or the other. This is including both. So this is again a collider path, And the variable can also be a member on S. So not only, so that was something that I didn't explain there, but the variable either is a collider or is a selection node, which is also a collider because it's going to be conditional. So it's kind of a case including both, including S.
It's the ancestry, right? I think, because S isn't an ancestor of anything else.
This is unobserved selection.
No, but the fact is that the collider path, so the variables, so that's the definition from here. Every collider is an ancestor of X or Y or a member of S.
Right.
So you don't need to be ancestor.
Right, that's why.
And
Yes.
The second example is the same thing. It's a member of S.
Yes,
collider.
that's true.
Yeah.
That's true. And then we have the definition of how can you convert a ADMG to a MAG. So basically, you follow the idea. You can just put together everything that I told you. So we don't want separate no adjacent edges. So we first create the adjacencies by pairs of variables that are either already connected or they are connected by an inducing path. So if they are in the ADMG connected by an edge or an inducing path, so an edge is kind of an inducing path already, then we are going to create adjacency in the MAG. So for every pair, A and B, so A, B, and V, right? So only considering the observed variables, the variables A and B, they are going to be adjacent in the MAG over G, if and only if there exists an inducing path between A and B relative to U and S. Basically, is the definition that we just talked. So because that condition that we want to preserve the pairwise Markov condition. So we need that every non-adjacent pair in the MAG is actually, they are pairs of variables that in any ADMG, they are M-separated or D-separated in the ADMG. So, so imagine if this is our ADMG, then the skeleton is going to be this one. The skeleton is just the undirected version, right, of the graph. And we just need to follow here. So the interesting case is this X, V4, and V3. So this is forming an inducing path because the edge here and this bidirected edge is forming a collider on V4, and V4 is an ancestor of V3. So this triplet cannot be separated. So X and V3 can never be separated, and that's why there is this edge between X and V3 in the MAG. The others are not interesting. So basically that exists already the edge, so you just put the edge there. And then we follow the idea of ancestrality. So the interpretation of these graphs are ancestral graphs, so they show ancestrality. So we add an edge from A to B if A is an ancestor of B or S. So you need to be careful with the S's. And as I said, the arrowheads, they represent no ancestrality. So B is a no ancestor of A or S. The other is symmetric. A and B, so there are two arrowheads here, so it's a bidirected edge because A is a no ancestor of B or S, and B is a no ancestor of A or S. And the undirected edge is because A is ancestor of B or S, and B is ancestor of A or S. So remember, tail means ancestor. No arrowhead means no ancestor, and that follows, right? And you just need to remember that the S exists here. It's a special case. In many cases, we are not going to even consider S's. Let's consider like the simplest case where there's no selection bias. Then in this case where no selection bias exists, then it's always like you just need to check ancestrality. This directed path is connecting one variable and the other. So here, let's see, V2 and X. V2 is not ancestor of X. X is not ancestor of V2. So what do you think is going to be this edge here, V2 and X? Bidirected. Yeah, complete everything here. What about X and V3? That's case here that was interesting. So X is ancestor of V3 through this directed path. So as is what I said before, an edge in this graph doesn't mean just an edge in the ADMG. It's just a directed path going from X to V3. And that's why it's represented here. Everything else, you don't need to care anymore about the bidirected edges. So you see that we moved to a space where we had bidirected edges, even like two edges, possibly between two edges, to a graph where we account for the existence of unmeasured confoundings, because we are talking about these inducing paths, so connections, even considering unmeasured confounders. So the implied condition independencies of this graph are the same as that one. If you go at home and you check, they are going to be exactly the same. But the space of graphs that I can create, like using the rules of a maximum ancestral graph, is so this space is much smaller than the other space where over the ADMGs. So we are going to work on the space of mags when we are going to do inferences with unmeasured confounders.
Just quick question: is ancestral relation just depends on this this arrows, one directional arrows, not this dashed?
Yes. So that's exactly what I said before. So basically all the independencies in the ADMG is going to be present in the mag. So I said, let's go home and do it. I did here already for you. And I just want to continue until 1 minute. So basically there are, as I said before, if we convert each of these ADMGs into a different mag, they, I don't know, what do you think? If you look at this picture, what you can conclude? So there are different threads, so there are 3 ADMGs. If you will apply the procedure, you can get these 3 mags. What can you tell about it?
Match the same.
They are exactly the same. So basically that's the collapsing thing that we are talking about as before, like different ADMGs, they are collapsing into the same mag, right? That's the idea of collapsibility. If we start counting, so that is actually a recurrence. It's kind of a code to compute the DEX or the mags. And if you see here how many mags I can produce over all this number of variables here, so in comparison to the DEG, is still higher, right? Then the space is bigger than the space of DEX, but in comparison to the ADMG is much smaller, like this or this, right? So this is still kind of very hard to compute, right? With 8 variables, but here it's starting to be feasible already, right? So if we wanted to count, of course we are not going to count here, don't worry. I just wanted to show one picture. So also, if you get different mags, you also can get the same implied condition independencies. So a few ADMGs can collapse in one mag, but there is still many mags that are representing the same set of condition dependencies. And that's what we're going to see in the next lecture, that so this is just an example where M1 and M2, they are equivalent, but not the M3. Let's see if I have a picture of, I want to go directly to the picture of a peg, this one here. So we are going to define next time what's a peg, which is the class that represents all the mags that are in the same equivalence class. So we are going to see this object in the end. Don't be scared. We are going there. But basically, this is represent the same idea as the CP-DEG for the Markovian models. Every time that I have an arrowhead, this arrowhead appears every time. So actually, here's a tail and an arrowhead. So appeared here, here, and here. This is also an invariancy, so appears here, here, and here. But there is this circle that could be anything. So for example, there is this arrowhead pointing here. So every time that there is at least one different mag, this is no longer an invariance, so it's going to be like represented as this. But we are going to characterize very well this object. It's not that simple as just replacing circles with arrowheads and it's going to work. It's not like this. So so you don't be scared. Well, the goal here is to learn this object. So there is an algorithm that we are going to learn. It's called FCI algorithm that's going to film data, is going to return this object. But it's important for you to understand what this object means, because from this object you can list in your mind all these possible mags and then corresponding ADMGs to know what's the possible models behind your data. Right, the ones that created your data. But inferences are going to be all from this object, because since we cannot learn everything that is not represented here, we need to consider the possibility that the model could be any of those. So we just can infer things that are invariant. So the effect of X on V3 or the effect of X on V4 is possible to compute here from this example. But you cannot say anything about the effect from V3 and V4 or from V1 and X. But parts of the model you can learn, and then you can infer effects from these parts. Got it. So I don't know what to do. Let's just stop here.